Hello everyone, I am Dr. Millie and you are watching Erudite classes, and today we will learn how the closed packing in the crystal take place. Means we are going to understand how the atoms connect with each other, they arrange themselves to make the huge crystals, and why we get the crystals in a variety of arrangement. That is, sometimes we get simple cubic, sometimes we get HCP, FCC, BCC. So what is the basic difference and how they are prepared? So that we are going to see. First of all, I am starting with the one directional arrangement, means starting of the crystal, starting of making of crystal takes place how? Let's see, I am having this ball here. This ball is indicating what? This ball is indicating atom. When one atom is connected with the another atom in a single direction, what we are doing is we are connecting one atom in a single direction, and this will give us a one directional arrangement, and this is what? Row made up by the atoms. So this is the row made up by atom. And now what will happen? We will convert it into 2D direction. In 2D direction, what is the possibility? Let's see. One possibility is I am taking another row of the same kind, and I am going to show you what are the possibilities. One possibility is that ball should be just after the ball. And this groove, can you see there gap in between the balls? This is the groove, okay, and here also it is a groove. So the possibility is that we are getting ball just after the ball, above the ball, and the groove above the groove. So I am setting it in such a way in the two dimensions so that one ball will lie on just after the ball, and one groove will lie on just after the groove. So here I am doing it, ball after ball, groove after groove. Can you understand now? So this is one possibility. Ball after ball, groove after groove. Ball after ball, groove after groove. Ball after ball, groove after groove. So this way, this is the one method you can arrange, you can set the second layer. Another option was, if I am having this if I am having this row and I am going to connect it with the another row. So there is another row. Now this time what I am doing is I am going to set it in such a way so that this ball and the groove of this second row will lie over each other, set over each other. Let's see how it happens. This ball and the groove of other. Look at this, ball and the groove, ball and the groove, ball and the groove. Can you see? Ball, groove, groove, ball, ball, groove, and groove making the ball. So can you see here very clearly that here in this case, in the second type of setting, you can see that the ball is lying on the groove of the other row and the groove is lying on the ball of the other row. So this is another kind of arrangement we are having here. I am joining third layer also and converting it into third layers also. So this is giving you two-dimensional arrangement where ball is lying over the row, over the groove, and groove is lying over the ball. So this is the next type of arrangement. So these are the two possibilities for the arrangement of second row, for the arrangement of crystal and setting up of second row. So this row is connecting this way, and this is called A type of arrangement, and this type of arrangement where the groove is lying above the ball and ball is lying above the groove, this is called AB type of arrangement. And what is the difference between these two? Can you see there? Here, if I am making another layer, let me show you. Now let's understand the difference between here. If I am picking any of the atom here, suppose I am picking this atom. Okay, if I see with how many atoms it is connected, it is touching. So can you tell me the number of atoms which this atom, central atom is touching? 1, 2, 3 and 4. In this particular system, in this particular type of arrangement, this central atom is connected with the 4 other atoms. So this is called its coordination number. in this case, in this type of AA type of arrangement, what is the coordination number of this particular sphere? It is 4. Okay, so actually what is coordination number? Coordination number of any constituent particle. Okay, coordination number of any constituent particle is the number of nearest atom which is there around this particle. Okay, so what is coordination number? Coordination number is the number of nearest atom around any constituent particle. If I pick any other atom also, suppose this time I am taking this, so 1, 2, 3, 4, there will be 4 atoms connecting with this particular constituent particle, and each atom in this particular type of arrangement will be connected with the 4 others. So the coordination number for the constituent particle in this particular type of arrangement will be 4. So this is called coordination number. If I go for the AB type of arrangement, let's see, this is your particle I am picking. Okay, now let's see how many atoms are there which are touching this particle. Number 1, 2, 3, 4, 5 and 6. So you can see here there are 6 particles which are touching the central one. What will be the coordination number? 6. So in this case, coordination number of this constituent particle is 6. Okay, but this is all about 2 type of arrangement. 2D arrangement. Now we are not in the third layer, we are not setting up the third layer. This 2D arrangement will give you the sheets, okay, the variety of sheets, and sheets over sheets will make the third dimension that will create the crystal, and 3D dimension will make a difference that how these are going to convert into simple cubic and FCP and FCC. So first of all I am talking about that how you are going to create the 3D arrangement. I am taking this one first because this is simple one, AA type of rows ko, AA type of first sheet ko. If I am setting the third layer of AA type over each other, what type of crystal I will get? Just assume I am making here AA type, ball over ball and groove over groove. So this is my AA type of 4 balls I have made here. Just after this, just at the back side of this, there will be one another ball. Just after this ball, there will be one another ball. Same way, after this ball, there will be one another ball. And after this ball, there will be another ball. Okay, I am picking the center of each ball. 1, iska center. This center, iska center will be here and iska center will be here. Same way, center, iska center here, iska center will be somewhat here. And I am connecting these centers. Can you understand? And this is what happening. Can you identify this structure? Yes, this is cube. No doubt this is cube. So when AAA type of arrangement, the sheets made up of AA type of arrangements are set over each other, we get cube crystals. That is, simple cubic crystals can be prepared by the arrangement of the AAA type of sheets over each other. So this is how the AAA arrangement give you the cube, simple cubic structure. This was about simple cubic. But when we keep this AB type of sheets over each other, what are the possibilities for making of crystal? Let us see that. Let us understand that. Before that, before arranging it, I am going to show you one thing here. Can you see there are triangles in this structure? Can you see there? All over the structure, whenever you go, you will get a triangle, isn't it? So these are the triangles over here, and obviously the 2 possibilities are, suppose I am keeping another layer. This is your first layer and this triangle of the first layer is there, and I am keeping the another layer above it in such a way so that the groove of this triangle is covered by one ball of the above layer. This is the possibility. What I am doing is that the lower 3 particles and their groove is there, and if I am adding one sheet over it, I am keeping that sheet in such a way so that that one ball of another triangle will be kept over this groove. This is the possibility. Let's see to it again. I am drawing it in a 3D dimension. Like I am going to show. अभी तो मैं आपको ऐसे दिखा रही हूँ. Can I do it this way so that you can understand? Let's see. These are the two balls here, and this one ball is at the back side. Okay. Now this is the groove created here. Okay. Now I am going to put one ball over this groove. So what will happen? That this groove will be covered by this ball and there will be a gap between, and this gap which will be formed after this keeping of second layer, this is called tetrahedral void. So basically this type of possibility is there. Another type of possibility which may be created here is that the 3 balls will be covered by another 3 balls. Means, let's see, 3 balls will be covered by another 3 balls. This is first layer, and I am keeping another 3 balls over it. So I am going to make it with the dot. So the another 3 balls will be like 1 ball, 2 ball and 3 ball. So 3 balls over 3 balls. This is the way the another type of groups will be created here. Okay, I am going to do it in this way so that I will draw the 3 balls like this and I will keep 3 more balls over it. So look at this again. 1, 2 and this another ball at the back side. You can understand, I think. And the another way is that I am going to keep the another balls. This is front ball this time. This is back side ball and this is also back side ball. So what I am going to do is I am going to keep these grooves, this groove and इनके बीच में यहाँ पर कहीं जो groove होगा, these groove will lie over each other, and this type of groove which will be formed after the arrangement, after the packing या setting of this second layer in this way, that is 3 over 3. This is called octahedral void. Okay, so this type of void which is formed by the setting of 3 balls over the 3 balls in the reverse direction. So can you see there, 1 ball, 3 ball, 1 ball, 2 ball and 2 ball, 1 ball. So in the opposite way, 2 balls in front, 1 ball in front. So if these three balls are kept over each other in this way, this is called octahedral void. The groove created, the gap created between these balls will be known as octahedral void. Now let us talk about the coordination number of these special voids. You can see here with how many balls this void is connected. 1, 2, 3 and 4. So because this void with this gap is connected with the 4 other balls, this void is having coordination number 4. So the coordination number for the tetrahedral void is 4. Okay. On the other hand side, can you tell me with how many balls this void is connected? 3 downside ball, 3 upside ball, and in between there is a void. So with how many balls it is connected? 6. So what is the coordination number? 6. So the coordination number 6 for the octahedral voids and the coordination number 4 for the tetrahedral void. I am going to show you octahedral void in a better way to visualize it, why it is actually called octahedral void. So I am going to draw it here, bigger one. So this is your 1 ball, second ball, third ball. Now I am going to keep 3 balls upside. So this is 1 ball, this is 2 ball and this one is 3. Okay, now I am going to take the center of these balls. This lower side ball, iska center this. This upper side ball, center is this, This upper side ball center is this, and this upper lower side ball center is this. I'm going to connect these centers. Okay, now take the center of this upside ball, the downside ball, and this upside ball, and connect this. Can you see there is a shape which is formed, which is octahedral. Octahedral means 8 faces are there, connected this way, up, down. Shape, just try to compare these two structure. First phase, second phase, third phase, fourth phase. 1, 2, 3, 4 phases upside, and 1, 2, 3 and 4 phases downside. And this is the reason this void is called octahedral void. So I hope it is now clear that if we keep second layer in the different way, we will be getting the different type of voids covered. So we will be creating two different type of voids called tetrahedral voids and octahedral voids. Then what? Then we are going to keep the another layer, third layer we are going to keep, and which will create the difference. And what we are going to do in the next step, we are going to cover whether only tetrahedral voids or we are going to include octahedral voids while setting the third layer over the first. That will create the difference in their crystal structure. So let us see now how the setting of third layer takes place and what type of crystals it will create. Let's start with it. Okay, ready to see how the third layer is kept to make the crystal? Let's do it. So we are going to have third layer and this will create difference. What are the possibilities? The possibilities are to cover tetrahedral voids only and to cover octahedral voids. In first case, I will be telling you that how the tetrahedral voids are covered. Okay, I'm starting from, this is your first layer. Can you understand this? This is your hexagon, 2D layer. This is the middle wall. First, 2, 3, 4, 5, 6. This middle wall connected with the 6 other balls. So I am talking about the hexagon sheet. Okay. And this hexagon sheet this center ball is connected with 3 balls. So this will lie here and this will create tetrahedral voids. Isn't it? In the same way, the third layer, this is your first layer A, this is another arrangement, means 3 above 1 we are getting. So this is B type of arrangement and we are going to place the third layer with just in parallel to the first layer. So this is the middle atom which will lie over this 3 ball. This will lie below the 3 balls and this will again cover tetrahedral void. So this is what? Third layer placed. And this type of arrangement where A is lying just, C is lying just parallel to A, just after the A. So ball and ball are lying over each other and this there is between 3 balls. I am going to show you in this better way. Better way how? Look at this. This connected. Now I think you can easily connect that this is your crystal hexagonal closed packing. Okay, so this is hexagonal closed packing. In between we have this. This is upper side ball, this is lower side ball, and this is the groove over which this ball is lying. And this is tetrahedral void. This is tetrahedral void. So here basically we are covering tetrahedral void. And this structure, this shape is called HCP crystal. So what is formed here? HCP type of crystal. Hexagonal closed packing. So this is hexagonal closed packing. If you go for the coordination number of the atoms in this particular type of packing. So I am going to concentrate on, suppose this is AB, AB, AB kind of. So AB matlab, can you see there? Ball, triangle, then ball, and then triangle. This will be the situation in this particular structure. So I am concentrating on this particular ball. Okay. So how many atoms, with how many atoms this ball is connected? 1, 2, 3, 4, 5, 6. So 6 from here, and 1, 2, 3 upside, 1, 2, 3 downside. So 6 plus 3 plus 3. We have got 12 atoms with which this ball, middle ball, is connected. So the coordination number of constituent particle in the HCP crystal is 12. So I hope it is clear to you. I can show you using the 3D structure also, so that you can make it very clear to you. So I am doing it here. Can you do? This is your atom. I am starting from here. Okay. This is your front atom. This is your middle atom, that is the center atom. This is your ball. At the side ball, this one and this one, and these are the atoms at the back side. So this is your structure, first layer, A type. Next, I am going to draw above the one ball. There are 3. So what they are? 1 ball, 2 ball, and 3rd ball. Again, I am going to keep this same type of arrangement above this. So what it is there? First ball, second ball, 3rd ball, 4th ball, middle ball, and backside ball. So this type of arrangement is taking place. This on the groove and this ball on the groove. So this will give you the tetrahedral arrangement. I hope it is very clear to you now that how the HCP crystal is formed by the A kind of arrangement. So this is called HCP layering, and this is how the HCP crystal is formed. And one more thing here, packing efficiency of this crystal is packing efficiency. Packing efficiency means how much space it is occupied, how efficiently this is packing the cube. That is called packing efficiency, and the packing efficiency of this type of HCP crystal is 74%. It is very nicely packed, and the examples are magnesium, zinc. Okay, there are many atoms which are showing this type of crystal. Magnesium hai, zinc hai, vanadium hai, and cadmium hai. These are the example of this type of packing. Okay, now let us talk about the second kind of arrangement. As I have told you, we can cover octahedral voids also. So how the octahedral voids are covered? When we keep the 3rd layer over the second. Let's understand that. So let's see how the octahedral voids are covered. Very simple. If you can understand that last one, it is again easy to understand. So I am going to draw a 3D structure just like the last one. I am going to draw the first layer, and the first layer will be the like 6 atoms I am going to draw covering this single atom, that is 1, 2. These are the side atoms. This is the middle one, and these are the back side atoms. I hope you can visualize this thing, that these are the 6 balls kept like this, and this is the central atom. I am going to shade it so that you can easily visualize that this is the central atom. Okay, now the second layer which will be kept, that is triangle. 1 ball, second ball, and 3rd ball. Okay, and the groove is here. 3rd ball, this is A, this is B type of. Now what we are going to do is, we are going to keep another 3 balls above these 3, but the difference will be they will be oriented in another direction. That is, ये back side ball is one. Here I am going to draw this back side ball in front, and the side balls will be this way. So I hope you are understanding. 3 plus 3, but in the reverse direction. So the groove between these two, the groove between here, there will be a groove now. The groove will lie over groove, and this will create what? Octahedral void. Isn't it? This is create what? This is creating what? Tetrahedral void. Now I am going to set the last layer over it. This is C kind of arrangement, A, B, C because it is reversed in direction. So C kind of arrangement is, here are the two balls. This is side ball. This is middle ball and the two balls. So this is A, B, C, and again I am repeating the same side of arrangement, that is groove will be covered by this central balls. Okay, so this is the central ball and this is again A. So what type of arrangement it is? A, B, C, A, B, C type of arrangement, and this type of arrangement will give you FCC crystal lattice. What type of crystal lattice? FCC crystal lattice. I'm going to show you how this gives you FCC kind of crystal lattice. I'm going to make it. Let's do it. So look at this very carefully. I'm drawing it. Parallel. Okay, so this is again, I'm connecting these with this. This is your Q. Okay, now I'm going to set the face center, the atom which are present at the center of the faces. 1, 2, 3. Iska middle will be here. Not here. It will be here. No, it is around here. Okay, now this face center or iska middle will be here somewhat. So 3 plus 3. Are you getting this? So this is called FCC. So one triangle you are getting here and one triangle you are getting here, and this is called FCC type of crystal. This is the part of first layer, this is the part of second layer, third layer, and again this is the ball which is making the center point of the last layer. Can you see there? One, this one, triangle, this one, another triangle, this one, and the ball, this one. So this is giving you FCC type of structure. So this FCC type of crystal structure will be formed by the arrangement of these atoms, A, B, C type of arrangement of these layers, A, B, C type of arrangement, and the covering of octahedral void is taking place there. Covering of octahedral voids. Okay, so you just remember one more thing, that is the efficiency of this crystal is also 74%. So HCP and FCC both are equally efficient. 74% is the efficiency of these two crystals. Second thing is that the coordination number, we can see the coordination number. So I am concentrating on ABC type of arrangement will be there. So obviously there will be one ball, these three balls downside. Okay, so I am concentrating on this. So this ball is connected with the 6 balls here, 3 balls here, and 3 balls here. So this also have coordination number 12. So the coordination number of this arrangement is also 12. The packing efficiency 74, coordination number 12, and one more thing, examples. Example of this type of crystal is copper, gold, nickel, etc. So these are the metals which settle themselves in this way. So this is HCP and FCC type of crystal packing. I hope this is very clear to you now, that how these tetrahedral voids and octahedral voids are formed. And in the next lecture, we will be discussing more about the tetrahedral voids and octahedral voids, and we will understand what is the relationship between the tetrahedral void, that is the radius here, the void which is created over there, this void, the radius of this void, and the radius of this atom. So this we are going to understand in the next video. I hope this video will be helpful for you to understand how these atoms connect with each other to form the layer, and then these layers are capped over each other to make these different type of crystals. What makes the difference and what creates the difference? So if you like this video, hit the like button, share it, and subscribe my channel. Thank you very much.